Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we have Ganesh visiting us from University of Washington. I'm extremely glad that he could make his this trip before he went to RPI. He graduated from Annamalai University in 1997 with a DE degree and a ME degree from University of Texas in 2002. And after that he joined University of Washington, the HID lab. He worked with Professor Blake on haptics. And he's just completed his doctoral work and will be going to RPI. Today he is going to give us a discussion and a presentation on his doctoral work. With that,
good afternoon, everyone. So my talk is going to be based on my dissertation work, but I'm trying to kind of outline the talk such that it's much more, it covers all the aspects, and later on if you have any specific questions I can delve into all the details. One of the first thing I would want to tell is when we interact with computers, we have voice recognition, vision through the monitor, we can have virtual reality goggles, but one of the interesting aspects that's missing is touch. In a day-to-day life, touch is very, very important, like a firm handshake or a hug. So touch plays a vital role. So my primary research is on haptics, which is a science of force feedback, and I'm particularly interested in networked haptic virtual environments. So why do we need that? You know, in the present age of globalization, so you could have multiple peoples working on a project situated around the globe or even across the United States. And it often gets really difficult to bring everyone in one place to get to make decisions. You could do is you can have like a teleconference or video conference where people can interact, but then it would be really ideal if you have a virtual reality systems where the users can actively interact in the application. There are certain applications that requires force feedback to get the maximum ultimate experience. Of course, it can be combined with audio and video. So it's not a standalone application itself, but it can augment the existing systems. Some of the applications that includes surgical training, maintenance procedure training, also one of the important aspect will be the network haptic games. Right now the gaming technologies lack in terms of force feedback, so it also applicable to gaming. So I can give you kind of over what's the basic idea behind. If we consider a very simple task, right, two users are just replacing a in screen, and then this involves two users, just two users have to bear the weight and then hold it in place. So it's just not only visual, but it also involves a lot of haptic cues. And if you want to train somebody else to do this task, and if you want to do a virtual reality environment to do this, it would be best only if you have haptic feedback. There are existing systems like Cave and other virtual reality systems where you can have a total immersive environment, but they lack force feedback. So the other aspect would be is even though this is a very, very simple application, you can also consider another one where, for example, in an industrial setting, if there is an accident, then you have to be transported in a stretcher. So the two users or two person have to carry on a stretcher over the complicated stairways or through some industrial setting. So you can also train your workforce on like contingencies without having them to experience that completely in a virtual reality setting. So in those cases, you might want to feel the force of lifting somebody on the stretcher, right? You don't have to imagine. So in those applications, force feedback also is very critical. As far as I said, when I said force feedback in virtual reality applications, there is also situations where the experts could be located in a different place or even a different office or geographically different location, and then all the users could be in different place, but the experts can always join in the simulation over the long distance and then participate in this virtual reality simulation. In that case, networked, both the virtual environments are networked, so there my research is directly applicable. So also, when I say it's applicable to games, I want to point out that I've been working on haptics for 5 years. So actually, I have my own haptic device. The technology has come to a point where you can get a device for $200, and it's called Norvin Falcon, and then you can actually play games with it. So for example, you can do bowling, you can feel the weight of the ball, then you can push it. So the momentum, acceleration, force, it's like a physically based, but you also totally involvement because you have the complete force feedback. So I also want to point out one thing is that imagine a situation where people are designing aircraft parts in a SolidWorks model, and then you have to make a design decision. Okay, I need to place this fire detector here, but then the fire detector needs maintenance like every n number of hours of flight hours. You don't want to put that in somewhere more complicated place that you need to remove or move through many different parts to reach that, right? Because that's not good. You want to do it in a minimal disturbance, like you want to go get access to the part that needs maintenance and get out. So in that case, you have to design that, right? So you can just log into a SolidWorks, and then the other user maybe is situated in Tokyo or Boston or anywhere, they could log in at the same time. You both can collaborate in the same virtual space and then make these design decisions. But of course, unlike just virtual reality applications, which are very passive, like even like one of the things is like watching a video, right? You are downloading a video from the server and watching it. So there is a lot of adaptive process goes on, and then you actually see the video, but then it's totally passive in the sense the only way you interact with them is through your vision. But when I say force feedback, you actually physically connect some part of your body to the device, and then you are moving it, right? And then you experience the force feedback. So there is a human in the loop which are actively engaged, and then there is a continuous energy that's transmitted. So stability is like one of the key things. You don't want the device to suddenly go like 20 newtons of force on you, and then your hands, you don't want to apply that much force on your hands suddenly. So there is a lot of careful design consideration that goes into designing such a system. And one of the keys, when I say networks, people in Seattle, another person collaborating in Boston, we have to overcome the network latency. So there is the minimum latency depending on the speed of light, which we cannot do anything about. So your system has to be capable of coping with latency. And also if you use internet, right, the regular internet, not only you are getting fixed latency, but also there is a jitter. Your delay is going to vary quite a bit. And of course, you can lose information, right? And then oftentimes your bandwidth might be restricted. And so these are some of the key things that your system should be resilient against, or you should design systems such that it shouldn't affect by all these factors. And then one of the key thing was how to maintain coherency in the simulation. As I said, when I worked, I gave several examples, gaming, and then one of the examples is having this CAD model where people want to collaborate on this virtual prototyping or maintenance task. So my research is primarily focused on the second application, which is having collaborative haptics application for CAD modeling and related application. And one of them is also surgery training, where you absolutely need to maintain coherency in the simulation. I'll later tell what I mean by coherency. So it's not very interesting when you have a networked system. It could be connected in two ways. One is like centralized or distributed, or another terminology is client server or the peer-to-peer. I'm going to talk about it a little bit later. But then the whole problem space of networked haptic virtual environment involves a lot of factors. One of them is force range. So for example, if you are using in gaming, right, often you might want to experience only impulse force, like you're playing a table tennis or a ping pong game. So you're experiencing every time when the ball hits your bat, you experience an impulsive force, and then there is no force after that. So the design for those and the force criteria are very different. Whereas if you're moving a big heavy object in a virtual environment, right, you might experience continuous force, larger amount of force. So the force range is one of the criteria. And the error tolerance, as I mentioned, for virtual prototyping and surgical simulations, you might want to minimize the error as much as possible. Irrespective of where the users are, the error has to be minimum. Whereas in gaming, it's okay. I mean, even if the error is large, you can always counteract, because more often you are experiencing force back only momentarily. There is no continuous force feedback. And then there is the aspect of mobility, like in CAD applications, it's often you can restrict the user to move slowly, or because they are doing some very delicate objects, trying to place an object inside this, like say part of the wing, or placing this fire detector. Whereas in gaming, right, if you're going to move slow, you're going to lose points. You got to move anywhere in the virtual space, hit an object, and things like that. So mobility is important, and also dexterity, which are related for like surgical simulation application or prototyping. You need highly dexterous manipulation, and then also the degrees of freedom. So you might want to experience 6 degrees of freedom often, because torque is an important aspect in mechanical things. But in gaming, you can get away with just 1 degree or 2 degrees of freedom. Also, computational complexity is one thing that we really need to keep track of. You don't want to build a system, then you need like a big server or some huge computational power to run your system. It might want to run in a simple PC or a cluster, small group of cluster. So I have said it in terms of graph. I chose three applications. One is entertainment by gaming, predominantly like haptics for gaming applications. Then I have had 2 delicate tasks which I'm interested. One is the surgery training. Another is a virtual assembly task which is related to CAD. And then I have plotted some of the criteria that I spoke on. For example, for force feedback, right? So in surgery, often the forces are low, because if you are experiencing too much force, then you are really damaging the tissues. So you don't really put too much force. But in CAD assembly tasks, often you might want to apply a lot of force to complete a task. In gaming, it varies depending upon what type of gaming you choose. As well as if you see, the gaming also requires really high mobility, whereas the virtual assembly task and surgery training, low mobility is fine. As well as the error tolerance should be really low for this task. So similarly, the way I talked on these few points, here I plotted the delay versus bandwidth. You don't want to design a game that occupies very large bandwidth, because you want people to use their DSL connection or at home and play games. You don't want them to have a very expensive internet connection. Whereas the virtual prototyping or surgery training often involves, in university or bigger companies, they have the luxury or they have the capability to get really dedicated internet connections. So they can have like large bandwidths. Similarly, I have plotted the computational complexity and versus degrees of freedom towards dexterity. So if you see that both the surgical training task and virtual assembly task always lies in higher degrees of freedom as well as higher dexterous manipulation. So I'm primarily focused on tasks in this block where it's high dexterous as well as high degree of freedom, but basically low error tolerance. That was one of my primary criteria. So whenever I talk about coherency in this talk, there is a very particular definition for that. Is, for example, if the users are manipulating a virtual object, so the user in Seattle as the virtual object in a screen, as well as the user say in Boston. So there are two copies of the same virtual objects. So my criteria is to minimize the error between the two copies. If I minimize the error, then there is always a coherency in the simulation, because I know exactly when I move the object or the person experiencing or seeing on the screen in Boston is also doing the same thing. So I have to minimize the error. So that's why I took the position coherency as a very important criteria. I also want to do it in a single instant of global time. It's pretty easy to do. Like you can almost synchronize your clocks using NTP or GPS, so that you can always maintain perfect clock synchronization between two computers. And then when you send packet information, you can timestamp it. So it's very easy to maintain coherency and also maintain time relevance. So why am I very interested in that? So I'm just giving a very, very simple example. Imagine like there is a CAD object, right? And then most of the time the object will have broader width, but then there may be areas where the width is very tiny, right? It may be like 0.3 millimeters, 0.2 millimeters, like you can have thin objects. So imagine the two users are moving an object, right? So whatever you're seeing is actually what one person is seeing in the virtual environment, and it's his copy of the virtual object, right? So this is the thin wall. Then the user 1 is located in Boston. User 2 is located in Seattle. So if you don't maintain coherency, right, the user on this side in Boston, they could go on this side of the wall, and then the user on this side in Seattle can go onto this side of the wall. Because the wall is so thin, if you don't maintain the coherency, then you can end up in the two copies of the simulation, like the virtual environment, will end up in two different sides of the thin wall. And then when you want to synchronize, one way to do is, oh, you know what, the virtual objects are two different locations. My objective is to minimize the error, so I can make it 0. The error is 0. But then since it's a physically based model, you cannot just penetrate through the wall. Like sometimes if you play multiplayer games, you can see sometimes objects disappear or appear through the wall, or like it defies physical principles. But you can't do it with haptic feedback, because you can't penetrate this wall, because it's a rigid wall, however thin it is. So you have to maintain the coherency in the simulation. So this is, which gives like a more convincing example. This is a typical CAD part of an aircraft model, like it's a very, very small snapshot. So it involves a lot of tubes and pipes and things. So my research was funded by Boeing. So with the courtesy of Boeing, I'm able to show this simple snapshot. And you can see if two users are manipulating, moving an object inside this virtual space, you don't want to end up being in one side of the tube or the other side of the tube or other side of the wall. So you might want to maintain the coherency to the entire simulation. And then the two users can take this object, maybe place it here, and say, oh, you know what, which is the best way to take it to there? Should we cross all these cables? Or if there is too many cables to cross, maybe we should put this here. So it's easier for the maintenance people to go and access that object. So those kind of design decisions could be made with a haptic device and using the CAD models as a virtual environment. So now I come back to the first part of the talk where I said about the networked haptic virtual environment can be classified into client-server and peer-to-peer. I'm very interested in peer-to-peer or distributed architecture because it's completely scalable. I can scale. And then each peer can multicast the information to every other peer, so that you can involve large number of peers in the simulation. Whereas in client server, you might need to have multiple servers, or you're really going to overload the server. So I'm very interested in first to answer, is haptic collaboration possible using a distributed architecture? So that most of my system work is based on distributed architecture, but I also use the client server architecture to compare the distributed scheme to see how well they compare. But if you remember when I said coherency, right, client server is the best method to maintain coherency because the server maintains the master copy of all the virtual object. So each client query the server, and server gives the current position of the virtual object. So always there is one location where the master copy of or the virtual object positions are maintained. So in that way, maintaining coherency is much more relevant and easier in client server. But then if the client has to work with the server, he has to first send the information to the server. Server sends the new information back to the client. So you have to do a round trip delay. So it's almost, if the delay is n milliseconds one way, you have 2n milliseconds before you actually realize the new position. Whereas in peer-to-peer, since each peer is multicasting the information, right? So each peer gets current information in n milliseconds of other peers' location if everyone is located n milliseconds apart. Also in client server, if client 3 is located further apart, like he has the maximum delay, then he will delay the entire simulation. Or if the client 1 is located right in the server or very close to server, the client 1 have a unique advantage because he can interact with the server and realize position much faster than the client 3. So you cannot maintain equality. Like you don't want, ideally you would want all the clients to feel the same thing. So those are the drawbacks of using client server scheme. So here I outlined the 3 virtual coupling schemes. I kind of outlined in the diagram that's kind of very standard or easy to understand in terms of haptics community, because it involves both mechanical aspect to it. So I can walk you through to understand this diagram. It's pretty easy in the sense, of course, communication channel is no need explanation. It's like it could be internet or local network or anything, and they are time varying delay. And then if you see the objects O11 and O12, those are the virtual copies of the object that users are interacting. So there is only one object, but right now it shows only 2 multi-user environment. So the object 11 and 12 are the 2 copies of the same object. And the user 1 is located here. He is interacting locally with this virtual object. User 2 is locally interacting with this virtual object. And also if you see, the virtual objects between themselves are connected by a spring and damper. So you can imagine this as copies of the 2 virtual objects, but they are connected by a spring and a damper. So when you push one object, the other object would move. Ideally, if you have an infinite stiffness, right, then whenever you move, it will track exactly. So that's the concept began. And also this is the peer-to-peer scheme, because you can have 3 users, 4 users, and you have to scale the number of the springs and dampers that you connect between the virtual objects. And there is a nice terminology for this. They are called virtual couplings, because they are not a real spring and damper, but they exist computationally. So they are called virtual couplings, but they actually couple between the virtual copies of the object. So in this way, you can maintain coherency in the simulation, because I can tune this springs and damper parameters so that the position error between object O1 and O12 are minimized. So I can always design the system such that the error is minimized. Right? This is one way to do the peer-to-peer system. The second virtual coupling I'm showing is a peer-to-peer system again, but it's slightly different in the sense each user has his own copy of the virtual object, but then each user's position is transmitted across the network. So if I am the user, I transmit my position across the network. Then if the other user on their side, they use their virtual object and then use current position and the position that obtained using the network, and then they calculate force locally. Similarly, the user 2 does the same thing on his side. So the connection is through the, if you see, this is the haptic handle. So this represents the haptic handle in the virtual environment. So the user's position is connected. So as long as two users maintain contact with the object, right? Because I'm touching this object, right? And then there is a copy of the same object in other user. He is also maintaining contact. So there is this continuous loop from this contact through this object and through this contact to that object. There is a continuous loop. So these two virtual objects will track each other. And this is applicable only when you have to maintain contact. So in some applications, like especially in CAD applications, you actually take an object, move it through a space and hold and put it in some other location. In those situations, you always maintain continuous contact. So in certain applications, it's directly applicable. The third one is the client server. So when I said the server has the copy of the virtual objects and server maintains the master copy, right? If you see here in the client server, this is the server, and then to make the matters much more simplified, the user 1 is located in the server, the user 2 is the client who experiences a delay. So if you see there is only one copy of the object which exists in the server. User 1, since he is already locally connected to the server, he experiences immediate force feedback through this virtual coupling. But the user 2 is the client, right? He could be situated in Boston. Every time when he has to experience force feedback, he has to send his position across the network to the server, and then server does the collision detection and calculates, based on the two users' position, this is the new updated position. Once that is done, the server sends the new position back to the client, right? But if you see, there is a local virtual coupling, and I have shown the virtual object just as a position, because if I am a client, even though I see a complete virtual object on my side and I'm interacting with it, its position doesn't going to change until the new position is updated through the network from the server. So for example, I'm pushing this object, I can push as hard as I want, but until my position is sent to the server and the server updates the position, it's not updated. So that's why he experienced the force feedback locally through this position constraint. But the good thing about this is, if the client is delayed so much, right, it takes 60 milliseconds to send the information to the server. So it takes 120 milliseconds for the new position to arrive. In the 120 milliseconds, if you don't give an immediate local force feedback loop, you could go into unstable situations. So in my design, there is this local virtual coupling give a high impedance path for the user. So the user always experience a local force feedback until new updated information comes from the server. So this is kind of a mechanical perspective of the schemes. If some people are very interested in control perspective, they want to see in terms of discrete time models, and then I actually have a slides later on. If you are really interested to see those system, I can talk about it later. Because basically all the systems all the three virtual coupling schemes I showed here are basically a multi-input, multi-output systems. You can have very formal control perspective too. So basically these three virtual couplings, which are two are peer-to-peer and one is client-server, and I know client-server is really good for maintaining position coherency. So my objective is to test these three schemes under various conditions and then see how well the distributed scheme compares to the client-server scheme or the centralized scheme. And then I want to see whether we can have a haptic collaboration using a distributed architecture. So in order to do that, of course, when I said I have to do it in a stable region, because when you interact with the haptic device, you have a direct energy interaction, so that when you have the energy interaction, you don't want the system to go unstable. So I tuned my system to be really act in a stable region. Then I tested my system in first a constant delay, which gives a baseline standard, then a time varying delay. When I said time varying delay, like the internet, so I used the actual internet and did global scale internet experiments at multi-rate. Why I am interested in multi-rate? Because for feeling really hot objects, stiffer objects, you need to maintain update rate at 1000 hertz, which is 1000 times per second. Imagine you are sending UDP packets at 1000 times per second of certain fixed size. You're quickly going to occupy a lot of bandwidth, and the bandwidth, not all the users might have the luxury of having that much bandwidth. So that at multi-rate, I can send the transmission at 100 hertz or 500 hertz, or like only every 10th packet is sent to the other user. In that case, I tested my system at multi-rate, so I can also objectively tell how the system performed at various transmission rates. Also, I'm very interested to see is like, once I present the results and things, somebody comes and say, oh, you know what, your experimental results involve this kind of network, and this network is like research network, they are gigabit network. What if I have to see if my system, how the system performance for say a low bandwidth DSL type of connection? So for that, I don't later on I'll say how I did my internet based experiment. So it would be really good if you have an emulator in your lab, so you can tune the emulator to create various network conditions, and then you can test the system. So as a third part, I also did the experiment with local network emulators, and then I have some results on that. Later on, I'm not going to really talk in detail about this because it's purely a control perspective, but time delay compensation is a very important aspect. When I said the networked applications have continuous energy transmission, so I said I tune my parameters so that my system is stable. You can also design your system such that they are asymptotically stable, like irrespective of whatever the time delay is, still your system is going to be stable. So there are already time delay compensation techniques that exist in teleoperation, and the good thing about my peer-to-peer scheme is it's exactly like a teleoperation system. So I can use this compensation techniques in my system, and then I can analyze the system performance. So in order to come up with an objective criteria and answers, right, you want to simplify as much as you could. If you have hundreds of knobs, and if you start tuning all these knobs, you don't know which is the right knob to set it to get the system results. So first, I simplified such that my system is only 1 degree of freedom, and then my virtual environment is very simple. It just has one virtual object, which is a cube, right? And then the two users are user 1 and user 2. This is the screenshot of the user 1's perspective. This is what user 1 sees in his screen. User 2 would see the same thing in his screen or in his computer monitor. And then the objective is to track this target. The target will move from center to the left, and then left to the right, and back to the center. So you have to track this target. So the target moves at a fixed speed, which is really slow, 1.33 millimeters per second. As I said initially, the problem space is really big. I mean, you can have a really high mobility application, but I'm not interested in that. I'm interested in much more dexterous but low mobility application. So it's still fine if you move at that slower speed. And then the cube is 30 millimeters width, and the target is 20 millimeters. The user 1 and user 2 will be making contact with the virtual object. So initially the cube will be white in color. As soon as the user touches the virtual object, and then when they apply the force, and if their force exceeds 10% of the maximum recommended value, which is 3.2 newtons for the haptic device I used, the color of the cube will turn to blue. The idea being that the two users are actively engaging in the experiment. So for example, you might get bored very well. I've seen during my experiment, sometimes subjects get really bored, so they might take the contact away, or they can make a contact but then they don't put any effort to push the virtual object. So in this case, when the force exceeds 10% of the recommended value, the color changes to blue. So I recommend my subjects that during the experiments, the color of the cube should be always maintained blue. The other aspect is when the force exceeds 3.2 newtons, which is the maximum recommended force for the phantom omni device that I use, the color of the cube will turn to red. So I'll tell my subjects, when the color turns to red, that means you are exceeding too much force. So push gently. So sometimes it might end up that they cannot track the target that well. So I also designed a software architecture for this entire collaborative haptic system. So basically it involves two standalone applications. I have a front end for graphics and user interface. So I used Qt because I develop applications across Windows and Linux platform. So I want something which can run on cross platform. So I used Qt as my front end. And then the Qt maintains the graphics and it updates the graphics, and then the haptic controller part, which is a standalone C++ application, which maintains the haptic controller, which maintains all the haptic interaction. And there is a lot more information. It's available in the slide. I don't want to go in depth for each block, but basically it supports both WinSock and the Berkeley socket. So you can just compile it in a Windows environment and then use it. So user is not restricted by any particular operating system. Also, if you see that the graphics application, the graphics update to the front, the interface is through a TCP connection, because you need to update the graphics at 30 Hertz. It's enough if you update at 30 Hertz. So even for those low update rates, you can update through a TCP connection. Whereas my haptic controller, the haptic data are transmitted at 1000 Hertz. And then I also did at 500 and 100 Hertz. So in those cases, I cannot really handle TCP using TCP IP. So I used UDP for the communication between peers and between server and the clients. So when I said global scale haptic collaboration, I had this dilemma when I started my research. I wanted to test in a realistic network, time varying delay network, but it will be really an interesting news article or something if I actually collaborate with somebody, say situated somewhere in Europe or something. I can tell him, oh, why don't you come on this time, let's collaborate and collect data. But then imagine there is like 8.5 hours or so time difference. We got two different time zones. Either I have to come really early morning to the lab, or he has to stay back really late. So it gets really complex to run human subject study if you have subjects spread across the continents. So ideally I want to build a system so that all the human subjects will be located in the same laboratory, and then so that they all in the same lab, in the same office space, so I can control all the aspects of the experiment equally among the subjects. At the same time, they also can experience realistic network conditions. So what I did is, of course, in the robotics community, you always have peers and friends. So many people came forward and willing to host a small program in the server. So I opened a particular port, UDP port, and then they ran this simple reflector program that I wrote, so that every time when the two subjects have to do the experiments, right, in sometimes they are connected locally within the lab, and other times their packets are routed through the internet through these various reflectors. And this is what you see, like between I had one in North Carolina State University, another is in Pontedera, Italy, which is a university called Scuola Superiore Santa Ana, and the packets go through very different research networks. Within the US, it goes through National Lambda Rail, and then I have a packet reflector hosted in the University of British Columbia, UBC. So they have a Canadian research network, and similar to the research network in US, Europe also has research network. So If you are interested, I can later give you the trace route to see how these packets are routed. It's very interesting. And then another quite an interesting thing is the server was a Windows machine in UBC, and Relay it was a Mac machine, and then in Pondicherry it was a Linux. So I had 3 different flavors on this. So this gives a very pictorial view of how the experiments are. There is always 2 subjects in my experiment, user 1 and user 2, and then they sit in the same lab and they do the experiment, and then depending on the network condition, depending on the conditions that during the experiments, the packets are routed all through the internet. So they experience real internet network conditions. So this is just a snapshot during one of the subject studies. So user 1 is always me. I'm the experimenter. User 2 is what I recruit different subjects, and then they do use human subject. It's basically a human subject study where I evaluate the performance. But if you see, we both are located in the same lab, just opposite desk. So I can start the experiment and stop the experiment. I can even communicate with them. In real life, you cannot really communicate with person in Italy unless you have a phone or something. So I'm not going to go in detail on how I did my experiments and stuff, because it will be really interesting for people who do a lot of human subject experiments. Always the user 1 is me, I'm the experimenter, and then user 2 is the recruited subjects. Usually it's part of the University of Washington students, staff and faculty. And then always the objective is to track the target. It's a 1 degree of freedom task. They track the target, and then I vary the number of trials and delay conditions and packet transmission rate based on what experiment I'm doing. And then I'm also testing, remember I'm also testing the 3 schemes, 2 peer-to-peer scheme and 1 client-server scheme. So yeah, all the schemes, delay and transmission rate are all randomized, and then during the experiment randomly those things are applied. So the user will never know what they are doing. They always do just the task they are asked to do. And then I add 10 subjects for each experiment. I did like up to 5 to 6 experiments for my research. One way to look at the task is, when I said the target moves from center to the left, back all the way center to the right, and then back to the center. It moves 1 degree of freedom. So if you plot it, this is how the target will look. And then I showed this cyan line shows the width of the target, and this dotted line shows the width of the cube. So if you see that the target stays within the width of the cube all the time. So the user are collaborating and maintaining such that the target stays within the cube, and then they are moving. This is just one trial from one of my experiments. So if you look at the plot, some of the interesting things you can look is, this is a time series plot from one trial of my experiment. Here I have compressed them into logarithmic scale to show the histogram of the delay, and then here it's like just a time series plot. So you can see that within the network, within national lambda rail, the spikes are much smaller. The delay values are almost, the network acted as well as the ideal network, like because it's a gigabit network. And then, but if you see the network to the Italy, which has 2 research networks, one in Europe and one in US, and also a transatlantic link, which is a bottleneck node. So you can see there's quite a few spikes. Each spike means there was a huge delay jump in the delay values. And then similarly for UBC2, we found a lot of spikes. So in these spikes translate to, if you plot the standard deviation, right? The standard deviation are much larger for delay value for network condition that existed outside of US gigabit network. Also here I showed that even though I didn't talk about controls perspective of my research, one thing is, I said I transmit UDP packets, right? But you are not, and then locally your program is running at 1000 hertz. Every 1 millisecond you want to query the new position. but you may not get the new position because of the time varying nature of the delay. You may not get new UDP packets at every instant of time, which is 1 millisecond clock. So I used zeroth order hold in my system, so that if you don't have any new data, you just hold the previous value until you get the new update. So here it shows that at 100 Hertz transmission rate, you always have this zeroth order hold for every 10 packets, and also you can see that it's varying because of time varying nature of delay. It's varying. And usually if you look at my publications and things, you see a lot of plots like this, which shows, like for example, this is the root mean square position error between the copies of the virtual object, and then I have scheme 1, scheme 2 and scheme 3, and then I plot this plots with standard deviation values, and then the inference for the real what this plot is saying. Like you can show many number of plots with lot of these bar graphs, but I also do statistical analysis. I do like repeated measures ANOVA, and then say if my results say if the error is, for example, if you see the position error is much smaller compared to scheme 2, but then are they statistically significant? That's how I come to my conclusion is, after I get the data, I also run statistical analysis to say, okay, this is not only the data analytically quantitatively showing difference in values, they are also statistically significant. One of the interesting aspects I saw is, even when I use this research network, if you see there is more packets that get lost in the transmission, because with UDP there is no guarantee that your packet will reach. So there is more packets that get lost for the delay condition which is corresponding to Italy. So because of the transatlantic leak and it goes through multiple backbones, there is more packets that get completely lost. But interestingly, if you see that even though I use UDP, I have far few out of sequence packets, because I am also interested in out of sequence packet. Because if I get a packet, right, the packet number is 100, and I am using the packet number 100, and if I get the packet number 98, it's no use for me because it's back in time. I'm not going to use that, so I just throw those packets. So there are far few out of sequence packets, but I got far more packets that get lost. In the beginning I said I'm very interested in answering a particular question, is haptic collaboration is possible using a distributed architecture. Out of all my results using the distributed architecture, based on my experiments, I get I can do a global scale haptic collaboration. Imagine I was doing routing packets to Italy and then back. So I was able to achieve collaboration with the error of 0.5 to 0.7 millimeters position errors, and for the transmission rate of 1200 Hertz. So most of the times this amount of error error tolerance or meets the criteria of collaborative application that includes virtual prototyping or CAD task. So if your CAD task can tolerate this much error, then you can use that peer-to-peer system to do collaboration tasks, so that you can always maintain coherency in the simulation. And then I also compared the performance, because in all my experiments I'm not only testing the distributed architecture, but I'm also testing the centralized architecture. So the centralized architecture will give the least position error, but then with the performance I got using the distributed architecture, which was from 0.5 to 0.7 millimeters, really comparable to the centralized. So if I have to use it, if there is an option, then I would use the distributed architecture rather than centralized architecture. This is one segment of the talk, and then probably I should stop here and maybe stop for questions, or should I go to the second? Yeah. Yeah, so one of the key is this is the root mean square position error, 0.5 to 0.7. It doesn't tell the whole story. I mean, because this is like a root mean square value of all the errors I calculated. But there is also another. I have several objective measures. I'm also one of the key objective measures is the peak position error. Any instant of time, what's the peak? If the peak position error is really large, then whatever you are saying, right, the collisions and everything will come into really play. So if you remember in the virtual coupling scheme I showed, where there is a direct coupling with the virtual objects, you can tune that parameter such that it minimizes the peak position error. That's what I did in my experiment. So the peak position error was very minimal. But also in this case, the user one has a local collision. So basically, user one, when he interacts with the virtual object, he collides with the virtual object. So there is one collision for that. There is also another collision where the virtual object can collide with any objects. Similarly, in another peer, you have to do the collision. So that's one of the, if you go to distributed architecture, then you're going to do more number of collisions across different of each peers. That's one of the drawback of using distributed architecture. But oftentimes you get a very decent sized computer that can tolerate or capable of doing this collision detections. Also, for example, there is a lot of research work that involves collisions of complex polygonal models or voxel models. One of them is developed at Boeing called VoxMap point shell, which can do which has a lot of pre-processing, but then at real time when you're running simulation, it can do collisions and update collision forces at 1000 Hertz. Because when you say collision, it's kind of very generic. There is two types of collision. One is collision for visual feedback, but in this case, I ideally want the collisions to respond at 1000 times per second. So you really want a really fast collision response. I'm going to just talk about another aspect of my work, which will be for next 10 minutes, and then probably I'll close in for more questions. So when I said I use the real internet to do the experiment, that's really cool. Like I can go and talk about, hey, I used the real internet. My friends hosted this packet reflectors. Then it's all my subjects experience real internet condition. But then if I have to, the network conditions are fixed, right? I'm using the academic gigabit network and things. I cannot force to route the packets to very different networks or so. But then you might want to test your system at the very low bandwidth connections or things. So if you are to follow my system, then you have to look for somebody who can host a packet reflector program that is connected to this low bandwidth network. Then I can run the experiments. Rather, you would want to use a network emulator in a laboratory setting such that the network emulator is guaranteed to provide many different network conditions. Then you can just, instead of routing the packets to the internet, the emulator creates various delay conditions. Then you can test the system in this. So during my second year of my thesis work, I just got into more of networks aspect because I want to see what can I do to create network emulator. So luckily, like network emulator already exists. There are many different flavors and things. I don't have to do anything from scratch. I chose to use NISTnet, which is a very popular network emulator. And then the real good thing is the data I got during the internet experiment, I can input the delay the histogram of the delay values in the emulator. Then I can say the emulator, okay, recreate the same condition. So for example, for the packet reflector location in Italy, if for example if the server dies, or like if the server is out for maintenance for a week, I don't have to wait for 1 week to continue my experiment. I can say if I'm guaranteed to create the same network condition in a laboratory setting, then I can just do it everything inside the laboratory. So basically this is the idea behind me using network emulator in my experiments. So there are several capabilities. Like a lot of people would know about network emulators, and then it can recreate various network conditions. You can also make it to change the bandwidth, and then you can recreate or you can mimic router congestions and so etc. etc. And as I said, why I need a network emulator, because I want to recreate various conditions, right? Lot of times, if you see in literature, people tend to use a simple Gaussian model or very simplified model for delay distribution and delay generation. But if you can do that in a network emulator and then test it, then you can convincingly say that, oh, if my system performs so and so in this local network condition, then it's going to perform the same thing when you actually connect to a live internet or similar network. And also it gives another one important aspect is repeatability. Like in many scientific work, you might want to recreate the same. If you want, all your experimental results should be repeatable, right? If I publish a paper and some graduate student in some other lab does the same thing like me, you should get the same result as what I did. So with network emulator, you can back or again and again you can create the same network conditions. And but a part of my work which I was very interested in the why I should use network emulator is because network condition directly affects several key things. One of them is stability. As I already talked about stability. The another thing is the tracking. The tracking is very similar to what I said in terms of coherency. So you want all the virtual objects to track each other. Another is a force reflection. One thing which I didn't really touched upon in today's talk is one thing is maintaining the system really stable. The other thing is another criteria, like somebody would say, hey, if you are in Boston and then I'm in Seattle, we are touching each other and then we are manipulating a robotic arm and pushing each other, there shouldn't be really any difference if you are located locally, right? Just the delay shouldn't change the way you feel the force. So that's called transparency in a system. So your system should be completely the transparency should be maintained irrespective of the delay. And often it's a trade-off between stability and transparency because you cannot really maintain both. You cannot satisfy both. So in my case, stability is much more higher criteria than transparency, but the network condition affects both. So I talked about most of the things in this, except that the work I did with network emulator, the application is not only to the network haptic virtual environments, but it also applicable to cooperating robots, a multi-user, multi-robot teleoperation. So I know there is a whole group of people working on wireless network emulation for multi-robot systems and so it has a direct application to many different robotics area. So I think it's a lot easier to show pictorially. It's like you do this this workstation maintains the packet reflector, so you send the packets from ear to ear and it routes back the packet, then you collect all the data, right? And then this is the kind of the same global scale network that I was using. And it's very interesting if you see for the delay distribution locally that exists within the gigabit network like National Lambda Rail, you will see only two really long spikes. One is across the mean delay value, and then there's the standard deviation is so less. So always you are expected your delay values to lie very close to the mean delay value. But for the packet transmission that across Italy, you often see it's significantly right tailed because you will end up that you are going to get lot of delay value over the mean delay value, as well as lot more delay values which lies towards the right side. That is, often when you see the packets, right, you will see that you see some packets close to the mean delay value, then suddenly you will see packets coming at larger delay values, and it's due to router fluctuation, and there is a lot more factors that go into why this distribution is like this. So I wanted to recreate the same thing in the network local emulator. So the NISnet was running in this box, and then the two workstations would just test to see whether it can recreate the same network condition. One thing I want to stress is NISnet was completely tested and there's a lot of users, but then you have to remember that I'm using NISnet for one specific condition where I use UDP packets and then I want to transmit at 1000 Hertz. Those conditions put very different criteria on how the NIST behaves. So I'm not going to go much in depth on what the details about implementation and experimentation, but because of UDP packets have you cannot maintain order because you get out of sequence packets, and then there is no retransmission. If you use NIST and then do the transmission at 1000 Hz, you end up lot more out of sequence packets. But if you use real internet, you don't get that many out of sequence packet. You get very unrealistic amount of out of sequence packet. So there is already, people have experienced that problem, and then there is some solutions for that. One is to maintain queuing discipline, so that instead of arbitrarily placing UDP packets in a queue, you have to place it such that the packets that in front of the queue has to exit before you can put something in front, so that it's an artificial way of maintaining less number of out of sequence packets. One thing I really want to tell in 2 slides is, I didn't stop just by testing the NIST whether it can tolerate 1000 Hz transmission rates for UDP haptic transmission rates, but I also tested this with 2 users, same experiment process, where all the experiments I did with internet, I also tried to recreate the same thing using the NIST in a laboratory setting, and then I collected a lot of objective data during the actual internet, and then when the subjects are doing the same experiment using the network emulator, then I get the same experimental objective data at the end of the experiment. Then I can compare these 2 data to see whether are they very different using NIST and then using the real internet. If they are very different, then maybe emulator is not a good idea. If they are very, very close and not much different, then you don't have to really use internet for testing. You can just use network emulator. So one of the key problem was the emulator was giving too many out of sequence packet, as well as lot of packet that gets lost in transmission is also pretty high in using emulator, which directly affected the performance of the distributed and centralized systems. So I think I would stop, because the other is a very different topic. I would want to stop with this conclusion about this experiment is, the emulator is suitable for lower packet transmission rate. What I mean by that is, when I did my experiment, I also tested the emulator for 3 packet transmission rates. One is 1000 Hz, 500 Hz, and 100 Hz. So for 100 Hz and 500 for 100 Hz, it actually perfectly matched the same performance measures I got using the internet using 100 Hz. So for lower packet transmission rates, you can also see that they kind of match in terms of our lost packets too. So for lower packet transmission rates, the emulator behaved very well like the internet for the haptic transmission rates and haptic data applications. So if you're using emulator, then you can use it for lower transmission rate. For 1000 Hz, so far I only tested NIST as the only emulator, and it's not really suitable for testing at 1000 Hz. Okay, I think I'll stop my talk here and then open for questions. Any? Yeah.
You have a cube and there's some mass involved. You have to involved with it. Did you ever take a Z transform on it and see the type forces on it, the discrete time form, what the delta between distribution changes and
Yeah. Yeah. So I think it's more, for example, this is kind of a discrete time model. The diagram I showed was a mechanical model where you have springs and dampers. This is more a controls perspective of what really that. Yeah. So basically you can derive a input output transformation for the system, and then you can define, you can always find the stability, right? You can always find the stability, and also since it's a discrete time system, it's also dependent on the sample rate. So I did that, and my parameters, like when I said the springs, right, the spring constant and damper values, they were all chosen such that the system is stable at 1000 hertz. So this is something, it's much more interesting for people who work a lot in controls perspective. Is you can also look at it in a very discrete time sense, and then you can derive very mathematically vigorous input output system. Basically you have two inputs and then you also have two outputs, because I'm interested in positions of the virtual object, and the two users inputs are also position. So you can have multi input multi output system, and then definitely it depends on the sample rate. So my system parameters are tuned such that at 1000 hertz they are stable, and then that's one of the, I think I answered your question.
At 1000 hertz, but then how about the latency in the network?
Yeah.
So from one end you could be sampling at 1000 hertz and the kind of process, but from the other end there is latency.
Yeah. So if you see that this is one end and this is the other end, two ends, right? Both these ends locally they run at 1000 hertz. There is a local loop that runs at 1000 hertz, but the transmission rate varies. As I said, 1000, 500 or 100. So but then I use, as I said, I use zeroth order hold to update the object. So there is locally you will get a new information, but then the way I updated the position is using zeroth order hold, and then that's why I have this transformation block. So when I incorporate stability criteria, it already includes transmission rates. That's why this is a multi-rate, multi-input, multi-output system. It's even though that's why I showed the figures with springs and damper, because it kind of removes the complexity of looking the system like this, and lot of times it's lot of easier for people to understand. Oh, you connect a spring and damper between two objects. They go, if you push on one, the other is to move. But then this is what really controlled perspective on that. Right now I don't have any such, because primarily I'm focused on solving like the basic problem. So I use UDP. So and I use really higher number port, but then I don't know, anyone can get that, and I have a publication which shows the data structure too. So but it's a research, so there is nothing very critical that's happening. But ultimately, if you have an application that involves SolidWorks, and then say Boeing is implemented this application and they collaborate between two locations, ultimately it needs to be really secure. So we might also have to see maybe different protocols so that it supports secure transmissions and things like that. One of them is the biggest challenge I faced was, like Boeing had this really very nice application where there's a full virtual environment application that from CAD models, it has a complete aircraft models and things, and then two users can collaborate on that. When I started my work, I actually started building my applications on their application, which involves humongous amount of source code and so many things. But then ultimately, right, I'm trying to solve a basic controls problem. So I really want to test something which involves not that many lines of code per se if you want to implement with code, but then it's conceptually also I want to test. So I want to make my system such that I know exactly what's happening everywhere. But so after, I believe it was 6-7 months after going through this code and trying to make it work, I said, okay, let's go back to the drawing board and say, you know what, this is not going to work. Rather it's much easy to create a very simple OpenGL application having a simple virtual object, and then it's very easy to create that, right? Then, but I have a complete control of that because I developed the entire software, so I know what's happening in every functions and every loops and things. So now I can conclusively say if my result is such that I'm 100% confident because I know in and out of my application. So I really learned to kind of simplify a complex. When you see something, it's really big, but then if you just slice through it and if you just think through it, you can make it much simpler than once I got the results right. Now these results could be translated to the system, but rather if I try to test their system based on my schemes, I would have spent much more, at least 1 more year trying to do that. Yeah, it's called Novint Falcon. It's primarily the Haptic device is primarily focused on gaming applications. It's called Novint Falcon. So it's a 3 degrees of freedom force feedback and 3 degrees of freedom input.